First of all, you try to understand this graph. This is basically graph of cos theta. So I'll do cos theta over here, and here is theta, which is a 0 degree. There is a pi by 2, 90 degree, and here minus pi by 2, 90 degree, minus 90 degree, and there is, let's say, here is pi, 180 degree, and here is another pi. This value goes maximum to 1 plus 1 and goes maximum to minimum to minus 1. And if you draw this graph, it looks something like this, correct? Right? So the below is minus 1, above is 1. So you see cos 0 is basically 1. You see cos 90 is basically 0. And you see cos 180 is usually minus 1. You can see over here minus 1, cos 80, minus 1, 0, 1, 90, 0, right? So you see all these values. Once the value is closer to 1, it means they are similar. That's why everywhere you try to see the dot product is around 9.4, they'll try to select it as similar. They say if the 3.2, they don't see it similar because it comes closer to 90 degree. If you try to imagine, if there are two vectors in the vector space, correct? Or these two just imagine these two like dots, right? If they are there, if try to just connect them, and this value theta, if imagine if the theta decreases, right? If try to decrease the theta, then what happens is this two comes very closer. See, I'm trying to decrease the theta, right? As soon as the theta decreases, we try to get closer and closer, and that's what we need. We try to understand that where this embeddings are sitting in the vector space, and if theta goes lower, then we understand that they are more closer and similar, and that's where these values come from. So if it's closer to 1, then it's more similar because the theta is 0, right? If it's closer to 0, then it means there is orthogonal, and that comes the concept of orthogonality, with the angle between them, these vector spaces are 90 degree. Then they cannot be similar, because these are the difference. Someone sits over here, someone sits over here. If their value goes to minus, right, like near minus, like let's say minus 0.98, for example, then what we understand is they are far apart. They are totally opposite. One vector sitting over here, one vector sitting over here, for example, if it's not minus 1 exactly. And that's the value of theta. That's how we try to understand if these vectors are similar or not. Hello everyone. So in this video, we'll discuss about embedding search, right? And we'll discuss about all these things. And then we'll talk about RAG, right? After RAG, then we'll discuss about enterprise RAG, where we'll talk about all these things: enterprise architecture, ingestion, multi-tenant RAG at scale, cost engineering, and everything, right? So let's dive into it, and let's start the first one, that is embeddings. So what is embedding? So a learned list of numbers. So you see learned list of numbers, right? Learned list of numbers. So whenever we write a sentence, let's say we say, how do I reset my password? Correct? How do I reset my password? This is a query, right? This is a query. And for each and every sentence, we convert into these numbers. So let's say D1 to D1536. These are the different dimension properties that has been given. There are fixed number like 7, I think 68, and then 1536, and then 3072, and 4000 something, and also 300 something, right? These are the different properties that you can select and you can generate the embeddings for. Once we try to generate the embeddings, let's say we use text small, right, embedding models, and this model is given by OpenAI. So that is already trained, and whenever we pass a sentence, that converts that into a number, something like this. So whichever embedding we select, let's say we say 1536, then this is the dimension that it generates. And these numbers are basically like 0, 1, 2, 0.31, 0.35, something like that. Like all these list of numbers gets generated for a sentence, right? And that gets stored. And these numbers are called embeddings, right? Hope you got the embedding point, right? So reset my password, then goes to the embedding model that this generates a number and points in the measuring space. Measuring space in sense we set inside a multi-dimensional space. So it could be something like this. Multi-dimensional space, something like this. Let's say we are talking in 3-dimensional right now. So if you are try to represent a line, so you need x, y, z, 3 different coordinates. So let's say 1, 2, 3, for example, the x value is 1, y value is 2, z value is 3. So this is how you represent a number in 3 dimensions. Similar way, if we talk about D 1536, then that main dimension will be there where the number will be represented. Right? You can see the query. And here D1 to D4 is basically about dimension, documents dimension. So document is also a text, correct? And that text also represented into a embeddings. That's really helpful in terms of finding the similarity, right? Because we can compare alike. You cannot compare non-like, right? You cannot compare animal with humans, right? So you can compare animals with animals. That's the reason we have to do both places embeddings at the time of questions, at the time of document, both places embeddings. Now, your mental model should sit on this tokens that we read, right? That is a language atom, correct? And this is generated with byte pair encoding that we have already understood. These tokens stay somewhere, and to represent and to find it out, we have token IDs, right? Like let's say 15, 70, 1048. For example, these tokens, language atoms, will be as a tokens from vector byte pair encoding, and they sit in an array, for example, and that array has a token IDs. With those token IDs, we try to find out tokens, correct? Each dimension is learn feature for of meaning non-human readable, because these are the numbers, so you cannot read those numbers. Now look at embedding models, right? So inside embedding models, you see there is separate trained model to produce embeddings. Its architecture and training decide vector size and what similar means, correct? So that text small embedding by OpenAI, right, generate those embeddings. So other providers like let's say AWS Titan, right, OpenAI, Anthropic, Gemini, all they provide these models so that you can pass your text and generate the embeddings, correct? Sentence versus document embeddings, different granularity when you try to convert one single sentence into an embedding and you try to do embedding of a bigger document, right? Query versus document, when you do a query, right, and also you do a document embeddings, right? Different model produces incompatible vectors, never miss them. Same model must embed both query and document, because if you try to embed into different models, then the vector embedding will be different, correct? Embeddings live in high dimensional space. That's where we talk about these different dimensions, 768 and 1536, even 3072, even 4000, something like 36 or something like that. Here is a number, right? Here you can see this embedding I given. More dimension is more nuance, bigger index, and slower search. So what happens is, let's say we have already understood cat, dog, tiger, and lion, and we have defined their properties, like let's say D1 property to D10 property, about having tail, about having fur, about having 4 legs, about having being pet or not, is wild or not. So this way we try to define the properties of these animals, and these numbers represent those properties. And once we try to create these numbers in terms of metrics, embeddings, then these embeddings will be learned by the models, and they try to differentiate or make similarity between cat and dog, tiger and lion on the basis of those numbers that we have already learned. That is, so for example, this is these, as soon as these matrices are available with us, is like these numbers are available with us, 0.35, 0.75, -1, 2, all these numbers, whenever these numbers are available with the matrix calculation, we can figure out, matrix calculation, we can figure out, right, similarity. How close two matrices are. Like, let's say there is a query and there is a document, how similar these two matrices are. With the help of these matrix, we calculation we do. Like we do, let's say, dot product, correct? We do cosine similarity, right? We do Euclidean distance. I'll tell you each and every one how we do all these calculations basically. So now, so more dimension, fewer dimension. So what happens is, if we try to do more dimension, let's say from 1536 we go around 3072, then what will happen, that these matrix size will increase. From earlier, let's say we had D1 to D10 for, let's say, defining cat, dog, tiger and lion, correct? So we had these 10 properties. Then if we increase this property to, let's say, 100, then we'll talk about the DNA of the animals, the family of the animals that belongs, then this keeps on increasing. And if you keep on increasing, then we'll try to get more and more similar answer or better answer or deep answer for those embeddings, right? But that's what is saying more dimension is more nuance. If we go 3072, the matrix will be bigger, correct? And then we'll be more deeply dive into the properties of the words or a sentence or a document chunk. But the problem is, once this matrix goes bigger, right, you have to do many more calculations, because dot product is there, cosine similarity is there, Euclidean distance is there. Then you have to take the complete 3072 matrix for one word, or let's say one sentence or one document string, and then multiply with other set of documents where you are trying to make similarity for, isn't it? So then it becomes slower, because you need more and more power to compute it, and that's why GPUs are needed, because they are very good in terms of parallel processing and faster processing. That's why NVIDIA is getting bigger and bigger day by day, right? Fewer dimension is cheaper, faster, less expensive. So in terms, once you try to build a product or a AI agents or a RAG application, then you should decide which kind of dimension I should select, rather than blindly going at 768 or 1536 or let's say 3072. You should decide which kind of dimension you should take, because as soon as the dimension goes bigger, these numbers goes bigger and your vectors search, similarity search goes slower. There is normalization and drift. Drift is basically re-embedding with the new model shifts the whole space. Like drift most of the time, in interviews also, the interviewer asks about drift. Drift is basically kind of, there is a method of data drift. This way I think I'll be able to explain you. So what happens, you build like, let's say, a machine learning model, correct, that takes an input data that produce an output, but it was trained on certain set of data, right, that you have decided in the test cases, correct? But let's suppose the input that is getting right now was not available in this test cases, and on these data the LLM was trained, the machine learning model was trained, the new data model hasn't seen before, so it will try to deviate from the answer. That is called data drift. You could say concept drift. That's happened, and that drift over here also. If you re-embedding with the new model, shift the whole space, because as soon as you try to select 786, the numbers goes lower. The properties goes to D1 to D768, not 786, 768, correct? And then again you try to do D1 to D1536, then it goes again bigger. That problem is creates in the vector space. The dimension gets slower, bigger. So that is a drift in these embedding models. Now let's talk about the vector mathematics. If you understood this vector mathematics once time, right, then you will never forget it, and you will be able to easily correlate the solutions and in RAG, right? So first of all, you try to understand this graph. This is basically graph of cos theta. So I'll do cos theta over here, and here is theta. which is a 0 degree, there is a pi by 2, 90 degree, and here minus pi by 2, 90 degree, minus 90 degree, and there is, let's say here is pi, 180 degree, and here is another pi. This value goes maximum to 1 plus 1 and goes maximum to minimum to minus 1. And if you draw this graph, it looks something like this, correct? Right? So the below is minus 1, above is 1. So you see cos 0 is basically 1. You see cos 90 is basically 0. And you see cos 180 is usually minus 1. You can see over here minus 1, cos 80, minus 1, 0, 1, 90, 0, right? So you see all these values. Once the value is closer to 1, it means they are similar. That's why everywhere you try to see the dot product is around 9.4, they'll try to select it as similar. They say if the 3.2, they don't see it similar because it comes closer to 90 degree. If you try to imagine, if there are two vectors in the vector space, correct? Or these two, just imagine these two like dots, right? If they are there, if try to just connect them, and this value theta, if imagine if the theta decreases, right? If try to decrease the theta, then what happens is this two comes very closer. See, I'm trying to decrease the theta, right? As soon as the theta decreases, we try to get closer and closer, and that's what we need. We try to understand that where this embeddings are sitting in the vector space, and if theta goes lower, then we understand that they are more closer and similar, and that's where these values come from. So if it's closer to 1, then it's more similar because the theta is 0, right? If it's closer to 0, then it means there is orthogonal, and that comes the concept of orthogonality, with the angle between them, these vector spaces are 90 degree. Then they cannot be similar, because these are the difference. Someone sits over here, someone sits over here. If their value goes to minus, right, like near minus, like let's say minus 0.98, for example, then what we understand is they are far apart. They are totally opposite. One vector sitting over here, one vector sitting over here, for example, if it's not minus 1 exactly. And that's the value of theta. That's how we try to understand if these vectors are similar or not. Now, so that is about theta. And similar way, dot product. So what happens is, in cosine similarity, when we try to do, you tell it to the interviewer that cosine similarity, we talk about angle and meaning. In dot product, we'll talk about angle plus magnitude. Like we try to calculate the magnitude of these vectors, and then we create the dot product, right? Dot product also represents that how closer the vectors are. And then Euclidean distance. This is basically try to calculate the distance between the two vectors. More closer the vectors are, more similar they are. So if you try to understand in let's say 2-dimensional space, right, or even 3-dimensional space, you have already know like this formula, when this is x and this is y, when we try to calculate two different distance between two different points, then I think we used to do x1 minus x2 ka whole square plus y1 minus y2 ka whole square and under root, and this was the distance that we used to calculate. I guess yeah, this was on it, or let's say it was like x1 minus y1, something like that, ka whole square plus x2 minus y2 ka whole square under root 2, right? And this was the distance that we used to get for these two vectors. If these distances are closer, means they are closer. If you try to apply all these together, like you do cosine, you do dot product, you do Euclidean, then you will get more similar vectors closer to each other, and that's how you calculate the similarity. Once we try to calculate the similarity in different words, like let's say there are one word A, B, C, D, E, and F. Like all these, you can see all these different words you try to create similarity, then you get a score. So let's say you have a query Q1, right, and you try to do dot product with A and Q1, B and Q1, correct, C and Q1, D and Q1, some similar way, and you try to get this value. Like say you get 9.3, you get 0.73, you get 0.26, you get minus 9.8, you get minus 6.8. Now you see, you try to calculate these, try to look at these numbers and see how they are connected, how these graphs making sense over here. If closer to 1, then it means they are similar because the angle between them is theta, and theta is 0 right now, near 0, because if they are in minus, then angle between them theta is 180 degree, totally apart. That is how you try to understand these ones. So if the measures are important, then dot product is there, cosine similarity is there, Euclidean distance is there, and Manhattan L1, like sum of per axis distance, is also becomes important in terms of trying to figure out the similarity between two vectors. And this is how you understand similarity between two vectors, correct? And this is, see, why these similarities between query and let's say a document where you're trying to search for is really important to calculate how closer they are, and they are in, let's say, 1536 number of these numbers and these numbers, but document could be D1 to let's say D100 from where we are trying to search for. And that's why these GPUs become really critical to do this matrix calculation, because to calculate these values. So why I'm trying to tell about matrix calculation, let's talk about in two dimensions. There is 2 4, there is B1 is 1 2, for example, and you need to calculate 1 2, then A into B, then you have to do 2 into 1, right, plus 4 into 2, correct, and then this 2 and this 8 and this comes 10, correct. This is the A into B of single 2-dimensional vectors or 2-dimensional embeddings. Now imagine if this becomes 1536 dimensional, this much bigger, and then you have to calculate between not one single matrix but one query, and there are multiple documents, and you have to multiply with all those documents and then figure out which is closer to 1, which is not closer to -1, which is closer to 0, then try to figure out the similarity between them, correct. That's why these GPUs and these matrix calculation becomes important, and this is the way, from starting of sentence that convert into tokens, that has representation of token IDs, then these tokens with byte pair encoding figured out as a language atoms, and then you do the embeddings, and then embeddings get indexed, and then you have these lots of embeddings, and you do matrix calculation, and you figure out the similarity with cosine similarity, you do dot product, you could do Euclidean distance, you do Manhattan L1. All these algorithms help us figure out the similarity, right? I think I hope I am able to tell you about all these. Now, curse of dimensionality is very high dimension, is distance concentrate. Yeah, everything starts to look equally for, which is why metric choice and good embeddings matter. Whenever you try to select a RAG application, try to figure out what kind of documents you are trying to select, what kind of query could be asked, then try to select the dimension of, let's say, 768, of 1536, of 3072, correct. Now, distance between points becomes similar, distance concentration. Naive nearest neighbor gets harder as DIMS grows. Good embeddings plus cosine keep direction meaningful. Motivates smart indexes, next topic, not brute force. So, if you try to understand, let's say there is Pinecone, right? Now, after this discussion, you will be able to read any paper of Pinecone given, right? How they generate their own vector database. So, what usually they do is they create slabs, right? So in the slabs, what they do is basically, once we try to start like they in their database, we try to index these embeddings, right? So they try to create slabs, they try to create, like, let's say centroid, what we call is, let's say there are 1 million documents, for example, 10 lakh documents, correct. On kind of second, 1000, lakh, 10 lakh. So I'll remove 1 0. These many documents are there. They try to figure out which document can come closer, and so they kind of create a centroid. So they try to put similar document at single place, because if the documents are similar, they will eventually go at a similar pace, and they try to figure out a centroid in each one of them. Like this is a centroid, for example, this is a centroid, and around these centroid, the most similar document will sit. So once we try to do search in it, they first figure out they don't. So it's become impossible to search in a million documents directly from a query. So they try to do first figure out which centroid is similar to this query that is usually searching for, and from that centroid they try again different type of embeddings in from that centroid, and that's how it becomes really faster in other ones. Now that same thing we are trying to look further, like when we try to understand about vector index and ANN, correct? So there is sparse versus dense search. If you understood it once, right? I'll promise you that you'll never forget it, correct? And you will be able to solve many possible questions in RAG, in terms of hallucination, in terms of vector embeddings. Your every doubt will be clear. You will watch it completely. Sparse is basically it's about keyword search. We used to do TF-IDF. If someone like if you are in machine learning background, then you understand TF-IDF. There is BM25, base mesh 25, correct? So this is here what we try to do is we just try to figure out text. We try to figure out language items. We don't do similarity. That is the difference. We don't do vector embedding. Like we don't create these embedding matrix, these numbers, and we don't do matrix calculation. It's all about searching those text, those keywords in set of text. That's what we do in BM25. This is BM25 is basically based match 25. Correct? 25 is a version of the algorithm that keep on improving. So this is, if you try to understand, you can get it from here, like embedding guide and Pinecone learn. So query comes over here, that gets converted to vector, that is semantic, that we understood about vector embeddings. Then we have this BM25, exact terms, IDs and codes, exact terms, IDs and code, and then we get that fusion, that output from the embedding, right? Now let's look at this one. Here, what happens is the semantic dense search. Let's say, how do I reset my password? If someone asks a question, right, and you have list of documents we're trying to search for, then the document says forget password, email a reset link ongoing. Look at the cosine similarity is coming 0.91, correct? Closer to 1. Understood? Closer to 1 means the angle between them is almost 0. 0 means they are sitting very close to each other. That's why this is there. Change your account password setting. This is coming 0.86, means little bit far away from the previous one, right? Someone coming 4.2, some saying 0.091. This is office repos Monday and after holiday. There is no similarity between this sentence and what user is trying to search for. Then if BM25 comes, right, if the BM25 comes, then you see what happens is, how do I reset my password? The keyword sparse search, BM25 versus cosine. Here, forget password, email reset link, login page, BM25 says 8.4 and cosine said 0.91. So we get more evidence that these documents are closer to what we are trying to search for, correct? So that's how it becomes really important to use these both lexical search and the semantic search if you're trying to figure out the similarity between the documents, correct? So BM25 rewards exact words. The router dog jumps to has to, because it literally contains reset. A lexical false positive semantic search avoids. D2 drops because it lacks the word reset, which is why you fuse that. This is wherever there is no reset, you have to avoid it, correct? And that's why these two documents have bigger values of BM25, like 8.4 and 6.7. So situation is exact term and SQ. Let's say you try to build some products where you try to figure out order IDs, or acronyms or code. Then you do BM25. When you do so, everywhere you don't have to apply vector embedding. You have to. So whenever you try to solve a problem in any kind of sector, trying to build agents or trying to build a problem, so you have to decide, is it able to solve it deterministic way, or we have to solve it in probabilistic way, correct? Like for example, if you talk about Netflix, right? If you talk about Netflix, so I don't think they use this LLMs to do the search, isn't it? Like let's say you search for Gadar in the movie in Netflix, So Netflix doesn't have Gadar movie, but they try to show similar movie, and they try to figure out Gadar means which Gadar they belongs, and they majorly I think they used to do word to vec. They do kind elastic search kind of searching. So you have to define which kind of method you have to go for, like deterministic method or probabilistic method, and decide which technique could win. Like dense, sparse, like this, like fuzzy natural language question, rare. So you have to make the decision in trying to build it on the basis of the requirement of the business, rather than just starting with an agent or try to build a prompt and try to clear the rack. No, that is not a good way. So now we try to understand vector indexes. And it's how a vector finds neighbors without comparing the query to every vector. So what happens is, as I was previously telling you, that they generate this centroid, right? Whenever we try to index these embeddings, correct? And these embeddings are kind of just numbers, and whenever they try to index it, they try to figure out one centroid in each of them that is the most similar amongst all of those data that is around them. And this is how they create a vector dimensional multi-dimensional space. When a query comes in, they have to jump within these, what do you call, within these centroid sphere where the embeddings are sitting. you know Maybe sometimes it will go above your head, but please focus on, I'll try to explain it to you, right? Then then these centroids are really important. These Once these centroids are there, you will be able to like traverse, like we used to do graph traversing, one graph to another graph to another graph, nodes, and we try to figure out the nearest neighbor, right? Many people ask them that why this algorithm DSA is really critical, and this is the reason DSA is really critical. You have to understand DSA, otherwise nothing will be able to, you will be able to understand in computer science or in software engineering or AI agents and everywhere, right? So DSA is really critical. It's really difficult, but it's really critical to understand, right? Then trying to figure out, first of all, whenever a query comes in, you have to figure out which kind of node you can jump for, and which kind of nodes you can jump for, which kind of centroid you can jump for, and from that centroid, which is other similar embedding that you have to search for, and then return it, right? It's not like, if let's say you have 1 billion of vectors, correct? Then if I do a query of a single vector, then I'm gonna do 1 billion search, like 1 billion dot products. That is impossible. That is never possible to do, and it's very compute and costly, etc. So we have to figure out of 1 billion, which is the most important numbers or vectors or embeddings that I should search for. Then I try to create different set of vectors, let's say a million vector centroid. And in this million vector centroid, I'll try to create 10,000 vector centroid and try to create 1,000 vector centroid, and then traverse from top to bottom like this. So 1 million to 10,000 to 1,000, and this 1,000 will try to do the vector similarity, and this 1,000 matrix is very possible with the current situation of LLM. So that's exactly, all these different algorithms are there, like brute force, you do compare all. That's what I'm talking about, a billion vector search. There is HNSW, layered proximity graph. So basically it's similar to graph search. You create multiple layers, you keep on moving from one layer to a different layer, and then the nodes becoming smaller. And now there is IBF. This is a cluster search, like the cluster that we are trying to communicate over here. There is product quantization, compares vector to same memory, compress vector to same memory. So you understand, right, already, that I have told you about these vector embeddings, correct? So if someone will ask you what is product quantization, correct? So this is an array, right? And this array contains 0 0.12, 0. Let's say 35, 0 0.78, like kind of 1536, correct? These numbers are represented as a float, and I think they need 32 bits to represent. What if we can generate int 8 bit? So can we write this number as 24, like with a similar kind of vector space, but in large, or let's say in smaller, maybe bit representation. Once the bit will be smaller, the vector will be kind of similar, the meanings will be similar, but the use of this memory, because we are using int 8 not 32-bit, that becomes smaller, and that's why they use product quantization. So I hope you are still following my point. Now let's try to do chunking strategy. Now the chunking strategy, what happens is too big, too small, just right. So there are, let's say, around 20 plus chunking methods that I have already discussed in this video. You can watch this video, right, and you will be able to understand it completely. In the chunking, what happens is you get a bigger document, right, and you have to like, let's say, understand these LLMs, and LLMs has to understand those words. So either you can pass the complete document, so there will be too much document to for it to understand, and there is a context limit, there is a token limit that we have already understood, that we cannot pass certain more token that we can pass, but that's why we have to chunk it, make it a smaller size. But again, there is a problem. If we do much more smaller size, then the context will be lost. If we do much more bigger size, then these token limits will be reached. Then we have to go in between them. We have to figure out like a medium size where we should not lose the context or the meaning of the chunks, and we should also have this tokens and limits maintained, correct? And that's why we apply these 20 different chunking techniques. So let's say there is a fixed size chunking, right? Fixed size chunking. What it does is, let's go to a sentence and try to, let's say, I say go and pick 100 characters or 100 characters, yes, and from these 100 characters build the chunk. That is fixed size chunking. There is a fixed size with overlap. So I do, let's say, let's do 100 and also do 20 overlap. So first I'll do 100 and then I'll again do 100, but I'll take 20 before from the previous sentence. 20 from the previous sentence and then these 100. You know, this way this overlap starts to happen. But the problem is this with fixed size chunking and fixed type overlap is we do not know from where the character will be cut. So the problem happens is the meanings get distorted, you know. Then we have this paragraph wise chunking. So what we do is we pick each and every paragraph and just make the chunk. No thinking, nothing at all. We do, let's say, section understanding, like how the sections are separated, like where is the heading, correct, where is the para, where is the sentence, and we keep on doing the chunking. There is, let's say, agentic chunking, correct. We pass the complete sentence or complete document to an agent, and that decides how to pick and which to pick. Like there is a semantic chunking, correct. Semantic chunking has two things, like there is a standard deviation, there is this percentile similarity, correct. So what happens in semantic, you try to, you know, understand these different sentences or chunks or paragraphs and then make a semantic meaning that how closer one paragraph could be a chunk, you know, how the closer or bigger context this paragraph contains, and then try to index it. And standard deviation is kind of number that you try to decide when to break them, when these similarity will be break. Like the way we just understood it, like we try to do cosine similarity and we do the calculation, and if it goes closer to 1, then we say that they are similar, and thus we keep on checking as a standard deviation. If you talk about percentile, then we say if these percentage numbers are similar, then pick it, right? That is a major difference, and these are the different lists of chunkings. There are other chunkings, I can tell you. There are chunkings like contextual retrieval chunking, right? Contextual retrieval chunking. You know, in here what happens is you pick a chunk, right? I have discussed in detail in that video. If you pick a chunk, right, and in the chunk that you try to do embedding, and then you put a summary, like what this chunk says, right, and then you try to index it. So basically what happens in the vector space, two things goes at the same time. There is a chunk of that content goes, and there is a summary of that chunk goes, and that get indexed, so that whenever you try to search, these vectors with the summary gets closer in hyperdimensional space, and the theta becomes closer. You know, you get near to one value, and then you try to return it. That is contextual retrieval. This is given by Anthropic, so you can see. So one giant block, too small, right overlap, the fixed size overlap, recursive structure, semantic split, document aware. These are different set of chunkings. You should watch that video, you'll be able to understand the complete set. Metadata filtering, the favorite topic I have. Here what happens is common metadata, you try to figure out token ID, the document ID, version, timestamp, department like HR department, accounts department, coding department, tech department, PM department, Figma department. All these things you can index, right? In a bigger company, you can have number of departments, permissions, doc type. Permissions is also really important. How, who can see these documents, So how do I reset my password? You say department is support, right? So what happens is it's all about funnel, correct? So let's say you have 1 million documents in a vector database, correct? Vector DB, and then these 1 million documents are so bigger, and we have to make it so smaller, so that the smaller chunks goes to the LLM to create the answer, correct? So we do this metadata filtering. First of all, we try to figure out if the content is about support, then we only pick support documents. So let's say from 1 million, we reach to, let's say, 1 lakh or 100,000. So let's say there are 100,000 support documents. That we did without even doing a vector embedding search. That we just did with only metadata filtering. We just apply support filter and only get the support filter. And then we keep on progressing. That is metadata filtering all about. Correct? It's about, what you do is, once you get a document, once you get a chunk, right? Once you get a PDF, once you get a doc, once you get a PPT, correct? You try to break them. You try to break them into smaller pieces. This is the character, correct? This is the sentences, group of sentences. And now this group of sentences is divided by those 20 plus chunking methods. And these 20 plus chunking methods, it should be decided on the basis of the business logic. Let's say it's you are talking in terms of financial documents, right? And if you talk about financial documents, there should be table aware chunking. You cannot, in financial documents, you cannot cut the table into half. Then it won't make a sense. You have to take the complete table, as a chunk and index it. Then you will be able to find a similar chunks, when you try to search. Let's say if you talk about database tables, right? Then you should try to search and do for those complete schema indexing, complete schema, not a single, like let's say 3-4 properties of a table into one chunk. You have to take complete chunk as a schema, schema is a complete chunk, right? So this way you kind of index the complete schema, right? So now you try to understand how this department and support, security, IT, HR has been given. Type is kind of knowledge base, and note is given. So this way, if you try to create metadata for a chunk, then you will drill down, basically create a funnel where you can cut the pieces, and try to do lexical search or try to apply metadata filtering without applying vector embedding. As vector embedding is costly, it will cost you tokens, correct? So, and this is what you can suggest to any person asking this kind of question, right? Because whenever you do vector search, correct, then you have to go through this cosine that I told you, right? You have to do with Euclidean distance, you have to go with dot product. And once all these happens, there will be matrix calculation, and that is costly. That will take your tokens, that will take your latency, right? But all these previous technology that we have used about lexical search, BM25, metadata filtering, they will not take it. So that would be the suggestion to anyone. Now, if we talk about how it's used pre-filter, post-filter means you have given the complete metadata, like let's say the JSON that you generate, there is your embeddings. Let's say there is a chunk, correct? Let's say this is a chunk, and for this chunk, you generate a JSON. So here is the numbers, and it's let's say 1536 dimension, and there you let's say you put a text, you also put type. So type is KB, knowledge base. You do department, you do support, correct? And then once you index these things, this JSON, so these JSON goes in numbers. Let's say it could be 100,000 JSONs for a PDF, as let's say the PDF is very big and you have decided to go ahead with agentic chunking, and you select those PDF document chunks and you try to index it, and this is how it will go to Pinecone. Later in the video, we'll see Pinecone also, and once we go to vector database, we'll understand how Pinecone works. Then you see these embeddings, right, get indexed in such a way, and once you try to do the search, so you don't go and figure out the vector embedding and do the matrix calculation and figure out the cosine similarity. You do this search first, and there is no involvement of tokens, there is no involvement of anything over here, so there is no involvement of vector embeddings, tokens, etc. There is only this type query, and an or query, you could say maximum, that we do in e-commerce businesses. We apply and an or query. Power citation is really important. Once we try to get this PDF into chunks, correct, then we should try to write it, that from which paragraph it comes from which page it's come from. And this is one of the solution of hallucination that we'll see later in the video, that citation is really important to make sure understand from which page, which paragraph, which section is coming from, so that once your RAG answers it, like once your vector database answers it, you can correlate with the actual answer. That's a citation. So this is how it becomes really important to use metadata, right? There is a parent-child retrieval. They retrieve a small, precise child chunks, but feed the model with a large content. Accurate match and full text. You can see there is a parent and child intensive. These there are multiple child chunks are available. These gets indexed and that will be returned. There is a re-ranking. That is really important. So once what re-ranking says that the second stage model rescores. Rescores. Many people ask why it's called re-ranking. Is because first we have already done search in vector database. Then again we are trying to do kind of a similarity. If the output that has been given from vector database similarity search is closer to the question asked by the user or not, that is re-ranking. The top candidates by reading query plus doc together, a big precision boost over raw vector order, right? So precision boost in the sense, once we have the query of the user and we did a document search like D1, D2 to let's say D100, right? And we got around 10 documents from the search. Even those 10 documents could be different. Like we already know there is similarity of 0.94, there is similarity of 9.1, there is similarity of 8.1, there is similarity of 0.76. We have to select one of the top similar, and we already know that it's come closer to 1, then its theta is almost going to 0, then it's more similar, but still there is other candidates that we can select for. There comes the re-ranking. There we try to understand the query of the user, these 100 outputs, and we try to compare and try to see, yes, these top 5 could be our answer, right? So hybrid retrieve, we already understand lexical search and metadata filtering, and then top 5 the cheap. Then we do the cross encoder re-ranking, keep top 5, and that we send to the LLM, and that is all about re-ranking, right? So there is by encoder and cross encoder. So by encoder represents query to vector and doc to vector, and there is cross encoder query plus doc, that becomes the score. The query that has been given, the doc that is getting produced, then we try to create the score. That is kind of cross encoder. That this is what majorly user do it, right? So by encoder is basically embeds query and doc separately, fast retrieval. That is a by encoder. And cross encoder is basically, so you can tell it that even in re-ranking you do by encoder versus cross encoder. Means there are two different techniques that you do in re-ranking. Interviewer or some person will be very happy to listen to the answer. So you see re-ranking, right? There are two parts, two techniques, by encoder and there is cross encoder. Correct. So in by encoder, what happens is query you create into vector, document that is already a vector, and embed separately, compare fast, because you have to compare these vectors now. Cross encoder is read together, accurate, slow, top 50 only. Let's say you get top 50 responses, and then you try to compare query plus doc. Like you have the query and you have the answer doc, and then you try to compare it. That is cross encoder. There is also this interaction. This is Colbert. This is the latest technology, I think, given by maybe maybe Google or Microsoft, someone. Yeah, it's a token level matching that they have given, right? Cohere, you already see BGE rankers are common of self choices that you can apply to do the. So these are all different type of algorithms and techniques. So this is makes DSA is really critical, because only having the vector database won't help you get faster result, and that's how that's where the use of data association algorithm and time and memory complexities are, correct. So context extension, you get it, that's very straightforward. Basically, after precise match, widen the window. Basically, window is trying to talk about the data, the content it will have, right? The content it gets from the vector database. The pull the neighboring chunk, the parent or the section context, so the model sees the whole picture. The LLM sees the whole picture. The previous and the next chunk's neighbor, parent document section, document level summary as a header, related metadata, again author. It's all about whatever chunks has been retrieved, what other parts we can get from that chunk, like from the PDF, from PDF citation, from PDF that page, from that paragraph. All these context expansion you can see to help LLM understand more better about it. Now we are starting about vector database. We understood the basic concept. So before we start to vector database, let's try to look at one paper research published by Pinecone. Correct. If I try to explain this paper to you, so first try to understand how this becomes really important. So why I'm pulling this up. So what is slab? So basically what happens, Pinecone uses log structured mud LSM tree approach to organize data. So whenever we use Pinecone, right? So we try to let's say use text small embedding, for example, of OpenAI, and we take something like this kind of content, any strategy chunk that we select, and we build the embeddings, right? These embeddings we select, let's say 1536, for example, and we try to index in metrics. But what happens if we try to we index 10 million of these embeddings, right? Then there is a query comes in, and this query has to search in these 10 millions, correct? So do you think that this query has to go to each and every 10 million vector and try to match it? That will become very costly for Pinecone, for us, latency and cost. Everything will increase. But that's what they are trying to build slabs for. So now here the concept comes of, let's say, vertical partitioning and horizontal partitioning of a database, and sorting of a database, replication of a database. That kind of things comes over here in Pinecone. So what they do is they try to create these labs. That's what I understood from their research paper. They try to create these labs, and in each of the slabs, they try to put similar kind of document in terms of, let's say, how they connect with each other in terms of their department. Let's say you do 10 million chunking, right? In these 10 million chunkings, there could be document that could be related to support, that could be related to HR, that could be related to account, that could be related to, let's say, banking, and that could be related to health. In only one company, in only one vector database that you're trying to build with Pinecone. They once you try to index it, they try to create these different sets, and they apply this NN technique that we just learned. The HNSW technique that we learned. The graph one that we learned. They try to build a centroid, like try to create one, for example, one centroid, and then outer they try to put the closure vector, because as soon as the vectors are closer, come closer, the theta gets decreased, and they'll sit closer if they are similar. And this is what happens in time of indexing. This doesn't happen at runtime. Once you try to index it, they create this, the Pinecone create this slab for you, so that once you do the search again, you don't have to go to 10 million. Let's say you get to 10,000. If it's about support, then you directly land over here, and there they apply this HNSW kind of concept, right? And you try to search, even if you try to dig deeper how they actually work. So there is a concept of bucket and mugs, etc. Like this is here we'll try to understand how. Let's give me 1 second. Let me make it a little bigger. Let me make it bigger. Right. So this is what happens here. You see, there is an application that you have that goes to the Pinecone API. Pinecone gives an REST API that you can communicate with it. You get the SDK of Pinecone, right? And as soon as you go to read the part, it goes to the query extractor, that goes to the in-memory, and here are the slabs, right? And from these slabs, right, you get your vector embedding search similarity, and you get the answer, right? So all these happens inside Pinecone. Once you have to push the embeddings, they do all these slabs creation for you, and then you get the data, right? Any other database you talk about, it works a similar way, and these, if you talk about these namespaces is like you try to define, let's say, if I talk about, there is a business, there is, let's say, support business, right? The support business has all list of documents, right? That has to be indexed into a RAG, into a database, not a RAG, don't call it RAG, I'll talk about RAG. So in the document database, and as soon as these are indexed over here inside this database, then you will be able to search, isn't it? That is, sorry, what I was saying, that is a namespace. You can call it a namespace, and this namespace is for a business, right? Now, if this support company has, let's say, 1,000 customers, each and every customer could have a different set of queries. They can ask about someone will ask about their payment, someone will ask about their subscription, someone will ask about their issue and bugs. Everyone will have their set of different query, and there could be, let's say, 1 year of conversation that will be happening. And these all conversation happens in a different namespace, and that becomes a user RAG, right? That is a major difference in namespaces. So now let's look at the more critical part. Yeah, this is the bucket. So what they say is they keep on filling, let's say, a set of glasses, and this set of glasses becomes a bucket, and this bucket becomes a very big jar. And this is how they start to store the data, and this is how the centroid becomes bigger and bigger. So most similar document come closer, and these are the slabs, maybe they call it, right? These, as soon as you try to index more and more vector embedding, so these matrices goes closer in that vector space and closer into that centroid. Centroid is basically center of that complete set of vector space. You can think of as galaxies. How there are billions of galaxies available, and then there are some center of the galaxy, and then all the planets are closer together. And there comes the DSA part, the algorithm part. If it becomes very difficult if you try to put everything in one machine. So that's why we do sorting. Sorting is basically you try to put the databases into multiple machines. They have their own CPUs, they have their own memory, and that is sorting. Partitioning is basically when you try to have a database, right, and you cut them in terms of certain rules, right? Like, let's say you try to define hash key, or let's say user IDs. Like, let's say I'll take 1 lakh user ID into one partition. You try to make them as, let's say, for example, a country-wise partitioning, for example. They try to use cardinal keys. So that's a different discussion altogether about partition and all. So, but this is how Pinecone is stored. Is they create the SARD 1, SARD 2. There is a client query comes in, there is a router happens, and then it gets get the answer from the vector space. And this is becomes really critical to index all these different set of what do you call indexes. Now let's try to come to our own one. There we try to learn. Just give me a minute. Let me refresh the page. Let me get my extension. Let me make it a full screen. Put it over here. Come here, right? And let's go to our section, embedding search and vector database. So now you see all these algorithms, right? This vector database, there is storage, then indexing and metadata, and then storage vectors. Index is HNSW. This is the graph traversal kind of algorithm where they try to figure out the most similar embeddings to next. So this is ANN. ANN search under the hood. There are like 4 or 5 algorithms that they apply. ANN is a like group of algorithm, you can say. Hop through a graph. Don't scan every vector. That's really important. You cannot go 10 million vectors and figure out. Correct. So that is becomes really critical in terms of building vector database and trying to imagine how the RAG would be happening, how the data that you are indexing, how you make your RAG faster, latency free, kind of. So common choices are PG vector. These are different set of vectors available. PG vectors, we see just Pinecone. There is Quadrant. There is Weaviate. There is this open search inside, let's say AWS. There is a Chroma also there, right? So pick on scale and latency needs. So this is really important. If let's say you're trying to build a product that is it's gonna sit closer to your, let's say you are in Mumbai, AP Southeast South 1 or 2, for example, then you try to do, let's say, Pinecone that is hosted inside AP South 1, or let's say you try to do an EC2 machine, and then you try to do Quadrant, correct, and try to scale it. Filtering and hybrid support, manage versus self-hosted. That's what I was telling you. Fit to stack like Postgres and PG vector. So this is how you try to select a vector database. And again, what is a vector database? You try to store those embeddings. So these 15 and 36 embeddings into a database, right? And that becomes a vector database. And these are the vectors, correct? Like similar way we had earlier, let's say RDBMS, Relational Database Management System, right? Where let's say we have Postgres, we have RDS, correct? We have MySQL, where we used to apply that select star query and a joins, etc. We used to do. Now, let's say if we have DynamoDB, correct? There we have complete NoSQL. Similar way, we have vector database, where we try to understand these similarities between the vectors. We do all these cosine similarity, we do dot products, we do Euclidean distance, we'll do Manhattan L1. We'll apply all these different logic to figure out the most similar vectors and give it to the answer. Like that is a vector database. That's where we store it. Now, let's move to RAG. So, one of the most important part that I want to tell you about what is RAG, correct? Why RAG exists. So first of all, we need to understand one sentence, that is RAG. Once you understand it, right, this will be very helpful. R for retrieval. Okay. A for, I hope nobody has told you before, augmented, and G for generation. Right. So retrieval is basically trying to retrieve the document. So you either apply semantic search, right, or you apply metadata filtering, or you apply BM25, or you apply hide. Yes, HYDE, no, hypothetical document embedding, or you apply, let's say, keyword search. That is a retrieval. Try to retrieve a document or a content from a vector database. Then augmented means the retrieved document goes to the LLM, correct? Right, means whatever you have retrieved again goes back to the LLM. So there is an LLM that first try to retrieve data from the vector database, and that data again goes to the LLM. That is augmentation, right? And that LLM generates the data. That is generation. So this is RAG, retrieval augmented generation, correct? Now hope you understand. So retrieval augmented feeds model your private phrase factual data at query time, fixing knowledge, cutoffs, hallucination, and context limit. And this is there is a paper that you can read about RAG here, how the RAG is started. They'll talk about parametric memory, non-parametric memory. Parametric memory is that model has, like the weights and parameters, and LLMs has, and non-parametric memory is the one we give through the embeddings to the LLM. So you ask a question that embeddings happen. So if I told you already, the similar dimension embeddings happen for both of them. You do the similar embedding for question, you do similar embedding for the chunks that you did from the document, and try to do the search, and that creates these things RAG. And this vector data that takes we search the data with retrieval, right, that goes into the LLM again, and that augmentation happens, and then generation will happen, and you get the answer. That is what RAG is. I hope you understood the RAG most importantly, right? Now there are some concepts that you should read. State knowledge, model do not know the recent private data. State knowledge, hallucination, ground assumptions in the real source. Like let's say you try to ask a very basic company information that is not available in LLM, so that you can do with RAG. Context limits, retrieve only what's relevant. Citation, I already told you that we have to represent from where these are coming from. If you try to understand the research paper, there are research paper that I have added over here. You can go with this research paper and you try to understand about RAG. The core equation is parametric memory that I have told you. Wait, what model learned? Like when we try to train the LLM. So you already know the LLM is based out of transformer. Transformer is based out of this understanding of tokens, their token IDs, their norms, their multi-head, right? Like how the verbs and adjectives are connected, how adverbs are connected, all these things that we have learned, how these complete transformer architecture works, and these encoders and decoders works. And once encoders and decoders are there, then there is generation happens, and that's how the parametric memory is being created. That is on in terms of weights biases, of billions of weights and biases, like that chunni, the bigger, smaller chunni there, that has that value when you try to put any data in it, and it produces an output over here, in terms of these weights that they have generated. So RNN is that recurrent neural network was there where we had to go sequentially, like we have to read token 1, then token 2, then token 3. But with transformer, we can read all of them parallelly and understand their attention and then generate the next token. That's how things are becoming in parametric memory, and that's how these weights and parameters are generated. Then with non-parametric memory, it's like the things that we try to generate with external data sources that was not available, or that is not that should not be available with LLM training, like company private data, like data that is produced after LLM has already trained, So that is non-parametric memory. There is a DPI, that is dense passage retrieval, learn to retrieve, RAG sequence and RAG token, use one versus many doc while generating. So this is all you can read from the research paper that I have added over here. You can go and check it, correct? Then we talk about RAG architecture. This is a very straightforward one because I've already told you two pipelines, this ingestion, offline build the index. So we try to take the document, we try to create the chunks, and these chunks gets embedded, like create the embeddings, and that gets stored. And this is how we do the index. And then we do the query that happens online and retrieve. That's R come from, right? And once we do the retrieve, we apply multiple mechanism to retrieve data from the databases, right? So load document, we create chunk, we do embedding, and that gets indexed in right DB. This indexing happens with ANN algorithms like HNSW, and there are many other algorithms that are available to make sure once we do the indexing, we can do the fast search, like graph search, build a centroid, like Pinecone, you have already seen the slabs, correct? Then once we do the query, then there is a question. In the question that we write, we can rewrite the question, and there are multiple ways to rewrite the question that we learn. And then retrieve the data, then re-rank it, and then the prompt comes in, and then LLM creates the answer. This is a complete architecture of a RAG, right? This is what happens once a RAG happens, right? Like retrieval-augmented generation happens, right? Then there is ingestion, load, chunk, embed, and index. There is query, write, embed, retrieve, re-rank, context, and LLM. Everything I told you about. Every advanced techniques plug into one of these stages. Absolutely. And answer shifts with citation. Citation, again, I'm just pushing more weight on. This is one of the most key technique to avoid being hallucination in the RAG, right? Now, naive RAG, you can see over here, there is a straightforward question that gets embedded. Do vector search, you get the top 5 chunks, and there is a prompt, and that goes to the LLM, and that gets an answer. That is a RAG. Again, I'm keep on telling you, R is for retrieval. We retrieve with multiple methods like vector embedding search, like we do semantic search, like hybrid search, lexical search, BM25, all those retrieval will do. Whatever retrieval comes from the embedding, that goes to the LLM, that is augmentation, and then generation will happen, that is RAG. That is a basic architecture of the RAG. Now let's talk about RAG failure modes. So this is really critical that you should understand. RAG failure modes could be in terms of latency, it could in terms of token cost, in terms of wrong answers. It means you call it generally hallucinations, right? So this you see over here, wrong and missing chunk, bad chunking or low recall. It's about how you do the proper chunking. In 20 plus chunking strategy, it's not like every time you should do agentic chunking, like every time you should do semantic chunking, or semantic chunking with standard deviation, or semantic chunking with percentile similarity. You try to understand the business first. then try to do chunking. Like let's say you can do one page chunk at a time. Like let's say we talked about databases. If you have to index the tables, then you take the complete table as a chunk, right? But that's what a problem could happen with these chunkings. There is semantic mismatch. There is a keyword mismatch. Ambiguous query that is there. Hallucination problems, context ignore problem, context confusion problem, citation mismatch. Again, citation comes over here. Citation is about how properly you have mentioned the metadata, like mention where this chunk is coming from. The cascade is like bad ingestion happens, then bad chunks creation, then bad embeddings happen, then bad retrieval happen, then bad context, and then bad answer. Everything is become bad. They start from, like, let's say this is a very good sentence, like bad ingestion, and then bad chunks, correct? So you ingestion is bad, like you take the bad PDF kind of PDF. From those bad PDF you create bad chunks. From those bad chunks, vector embeddings are bad. Vector embeddings, then retrieval will be bad, then context will be bad, then answer will be bad. That's how you should understand it properly, where these rags can fail altogether. Now try to understand about query transformation. Query is basically whatever question we ask to the LLM, right? And once there is LLM, then there is RAG, right? So that we have the non-parametric memory. LLM has a parametric memory. This has a non-parametric memory. That memory that LLM could not get at the time of training. RAG is there, then we retrieve, we augment, and we generate, correct? And the query transformation is, once we try to do the retrieval, we do a better retrieval, right? And one of the technique is query transformation. Like the query that user is asking, we try to transform the query to make it better. Like, what about its pricing? Rewrite by LLM, pricing of the pro plan, plus chat history. Like we understand the chat history of the user, what earlier it was communicating about which product, and then try to rewrite the query and ask about pricing of the pro plan. So it's about rewriting self-contained resolve pronouns, expensive, add synonyms and related terms. Like what about pricing of, let's say, AWS EC2 machine. This is what being added if the context is there. So it's query expensive, correct? Decomposition of the query. Try to decompose the query into multiple queries. You try to make query in such a way that each and every decomposition of the query has its own meaning, and try to find the answer, right? Routing and classification on the basis of the query understanding that user is pushing to the RAG or to the agents, right? You try to decompose it, and then or sorry, route it to multiple places, or classify it what kind of query you're trying to ask. Step back, ask a broader question first. Means again going back to the user and asking a better question. There is multi-query concept that you can understand. In multi-query concept, what happens? Generate several phrasing, retrieve for each, and merge, right? So one question is there, you try to do variation A, variation B, variation C. For each and every variation, you try to generate the answer, you try to search the RAG, and then merge it, and then dedupe, and then re-rank, and then give it to answer to the user. So different wordings surface different chunks. Absolutely. If I have one question and I try to ask three similar meaning of three type of question, and then generate the embeddings, then there would be many more vector similar chunkings will be available with me for the generation, right? Boost recalls for ambiguous question, union dedupe, and re-rank merge. That you already understand. Now HYD, to try to understand that you have seen many a time. This is hypothetical time document embedding. What they do is basically there is a question that user asks, right? The question is being asked. Now they create a fake ideal answer, right, by the LLM before it's going inside the RAG pipeline. RAG means Retrieval-Augmented Generation. So retrieval hasn't happened yet. Once this fake ideal answer generated, then we generate embedding for that fake ideal answer, and that embedding gets searched in as a RAG. Like retrieval happens and augmentation happens and generation happens. Like embed the answer, search with the answer, and you imagine the answer already and you try to search that embedding answer, and then you get a better embeddings. That is hyper document embedding. That's a really important topic. Retrieval strategies are there that we have already. This all about R list. There is a top case, similarity threshold, hybrid means lexical plus similarity search. Similarity is a vector embedding. Top key is a top key parameters are returning. Multi-query is about updating the query into multiple one. Metadata filtering we have already understood about adding the metadata for each and every one chunks that we put in, and then apply and or query and then get it. Hybrid we have already understood. Hybrid is basically lexical, right? Lexical is BM25 or TF-IDF. It's all about keyword. It's all about keyword, TF-IDF, and then there is semantic. It's all about vector embedding, similarity, cosine, dot product, Euclidean, etc. There is one other one is similarity threshold. How closer the vectors are together, the theta is there, right? There is parent retrieval. Parent retrieval is you do complete chunking, you search for the uh, child chunk and then retrieve the parent, that we have understood. Contextual, right? Context, everything about context retrieval chunking that we have learned. Multi-vector, hierarchical, query routing, all of these things we have learned. So this is these are the different retrieval strategy, and everything starts from RAG. First retrieval happens, then augmentation happens, then generation happens. Correct? That is important. Now you in the previous video we have understood about prompt engineering, and now we'll talk about context engineering. So we saw in prompt engineering that how better prompt we can do, how better we can engineer the prompt so that it can become the best prompt, right? In terms of, let's say, system prompt, in terms of user prompt, in terms of skills, in terms of tool calling, right? In terms of RAG, how better we can build this prompt, and that was prompt engineering. Similar way, there is a context engineering, right? How better, and here also we try to talk about how to make it better in terms of token usage, isn't it? Because token usage is the main bigger problem that all these enterprise companies will have, and about latency, right? So this context engineering is like from 30 chunks to a tight context, like retrieve 30 chunks, there is deduplication happen, re-ranking will happen, like by encoders and cross encoders that we haven't read. There is a compression happen, then they will select, right? There is a 20k tokens order, then LLM will be given answer, right? That is the generation part. So the levers are lost in the middle. Models ignore the center, put key into the fact at the edges. Compression and summarization, shrink chunks before the prompt. Ordering and dedupe is highest signal first, no repeats. Token budget, that is a relevance beats volume and save cost. That is all we do in context engineering. Like for example, there is a context pruning that happens. We try to index all the context that we have got inside the user namespace that we have understood in while we are reading about Pinecone, and then as soon as the similarity matches, we try to retrieve only those chunks, right? Like the user message and the model response that we get, right? So that is all context engineering that we do. It's context engineering about how better you can make the context in terms of token cost, in terms of latency, in terms of hallucination, right? The advanced RAG variants, like these are the buzzwords like weak and wrong retrieval that you know, that is a corrective RAG. When weak and wrong retrieval happens, you try to do corrective RAG. There is a complex multi-step question, then you do agentic RAG. Means agent decide when the answer is completed. Correct. There is a racing across doc that you do graph RAG. It's about figuring out the entities into the documents, and then you try to build it. Retrieval sometimes unnecessary, adaptive or self RAG, right? Reusable composite RAG, that is a modular RAG. So corrective RAG is grade before you answer. We'll just try to understand each one of them parallelly, means one by one, right? So these are the different type of RAGs. So there is a RAG, and once you do the engineering, I'll call it RAG engineering here. RAG engineering, right? And that's what we are trying to do here is the corrective RAG. So grade before you answer. So there is a retrieval happening. Grade docs is relevant, good, then generate, weak, then research. That is corrective RAG. You have to correct it until unless you get the better answer. There is agentic RAG. The agent decide if the output that retrieval has been given is correct or not. Correct. So then which source the agent decides retrieve, if enough, then answer inside. Otherwise, which source keep on happening, then you get the answer, right? There is kind of adaptive RAG. So just keep on telling you so that you understand it completely, right? There is a adaptive rack, effort by difficulty. Router, how hard, like simple, medium, complex. So here we'll go agentic multi-step. Medium we'll go one retrieval. We'll go kind of answer directly. That is adaptive rack. Means we try to grade the questions. That is coming to the LLM. To the LLM, we try to grade it. Once we understood that it cannot answered by a simple query, then we should go ahead with a medium. Like we try to do one or two retrieval, and then we go ahead with complex one. We'll try to do the agentic one. There is a graph rack relationship. It's about entity relationship. It's about company. It's about person, people, department. So Ekme signed a contract, and this is, you can see, these are the edges where we try to tell what exactly how they are connected with each other. Neo4j is one of the leading player who's trying to build this kind of graph, because they are a graph database. So this is how they are building it. Contract has clause 7 owns, and this becomes really faster and easy for LLMs to grab these information and search. Even because search is, everything is inside the RAG is SNSW and other ANN algorithms that is being applied. To do the partition, to try to build a centroid and get the answer. That's where he is. Here we have this edge also identified. Correct. So this is another RAG. Now let's try to understand the hallucination. So hallucination, if you see, RAG reduces hallucination but never removes it. Production system stack defense across retrieval, prompting, and verification. There are two papers that you can read here. Then layers that reduces hallucination. So the first one is better retrieval. So retrieval is not a single part, it's kind of a hybrid search. I keep on telling you so that you remember it all the time. Hybrid search, there is semantic similarity. There is hybrid, inside hybrid only BM25 lexical search, you could say. There is metadata filtering. There is query writing. So if you talk about query writing, there are multiple types of query writing. There is hypothetical document embedding, that like we try to get the answer and then do it, and then from a query we generate a multi-query, right? From query to multi-query, there are decomposition of the query. There is, let's say, enhancement in the query. That's all we do in the query. So there are multiple ways we can do the retrieval. Answer only from the context. There is a citation. So there is answer only. Means there is citation that we can add in all the terms of PDFs, documented where this is coming from. This is 1, 2, this is 3. So someone will ask, this is the way you can answer it. Like you start with better retrieval, then you talk about retrieval, how you do the retrieval. Once you go to the query, then you talk about how better you do with the query. Then try to do with the answer, then talk about context, how the context could be closer to what you want to answer. There is a require citation, refuse if unsupported. There is a grounding check, like grounding check. Once answer is generated, then you do query and answer check if whatever RAG has been generated, same answer LLM is producing or not. Because what happens is, once you do retrieval, right, then augmentation happens. Then whatever retrieval has been done, that goes to the LLM, right? And once it goes to the LLM, then the generation will happen. If let's say the generation was done, but that is not similar to what was retrieved, then there is a problem. If generation is done and it doesn't contain what was retrieved, then there is a problem, and that is checked by groundness. There is a faithfulness evaluation that happens. School every answer. There is a corrective RAG that you research on weak docs that we have understood. There are multiple ways of RAG that we can apply, that RAG, right? So the full toolkit is retrieval, hybrid, rerank. So there is rerank also. So that is come under retrieval also. So you can say rerank, or you can see rerank comes after generation, because once the generation will happen, or it can come after. Yeah, it will come in retrieval itself, right? That does the reranking of which one is closer. So retrieval reranking will come under better retrieval. there is a prompt. The prompt is really important because it's the instruction that we send to the LLM. So answer only from the context, it absent says so. That is about grounding, being grounded and being abstaining. Like if RAG has returned something and LLM is answering different thing, that you don't have to tell it to the user or to the customer. Citation, I already told you. Grounding check, verify each claim maps to the chunk. Chunk is the retrieval, right? And then it goes to the LLM. Then generation will happen. The generation and the chunk should match, right? Let us say chunk says 15 days leave, right? And somehow LLM generation says 30 days leave, then that is a totally different answer, correct? Then we have to avoid this. Then there is faithfulness evaluation, score groundedness on every answer, confidence and abstain. And this is what they ask: faithfulness, precision, recall. Once you try to go ahead with the evaluation of RAG, someone will ask, how do you evaluate RAG? And these are the main things that you will evaluate RAG. Now let's move to the next topic, that is citation and grounding. I think I've already covered it. So, but once again, so this claim, evidence mapping per sentence, where exactly the sentence is coming from where, which paragraph, which section, which table this is coming from. Citation correctness, right source, completeness, all claim covered. So that if someone will say that your RAG is hallucinating and you prepare the answer and you write that this is a section 4.5 para, and you go to the para and the same answer matches, then there is no hallucination happening. Flag unsupported claims and rank resolve. Now we'll look at rank evaluation, correct? So if someone will ask, you can read this and this video, paper basically, or article. So retrieval metrics are, did we fetch the right info or not? That's how we try to understand RAG evaluation, because R comes first. If retrieval is bad, then A and G will be all definitely bad. That's for sure. Like if R retrieval is bad, then that will be going to the LLM and that will go to the generation part. So the first metric is recall @k. Are the needed chunks in the top key? That is needed. That is the first metric that we should take care of. If someone will ask, that is recall key, that will check that the chunk that has been retrieved is in the top key or not. Precision @k. How much top key is relevant that the content desert is coming. MRR, how high is the first correct hit, right? And DCG, are relevant docs ranked near top. So now these are the different metrics, and these are the metrics that is being used in Ragas. So Ragas evaluation framework we'll see. So they are for the RAG evaluation, and they build all these different type of metrics to evaluate RAG. Then also they come they add it into different this kind of term, where they say faithfulness, answer relevance, context relevance, citation correction. These four are the main metric that these Ragas and other evaluation frameworks calculate. Is every faithfulness, is every claim grounded in the context? Does it address the question? Like if I am trying to teach it to a topic, and if I'm able to connect every dots, then I'm able to give you an answer. That's what answer relevance means, right? Context, was the retrieved context on the topic? Do cited source support the claim? All these things are there in terms of evaluation of the RAG. Then there comes observability, where you try to observe, trace every stage with timings, scores, tokens, and costs. So you remember timings, right? How much time it takes to retrieve it, augment it, and generate it. That is timing. There is a score. How score is like similar, like 9.8, 0.83, something like that. Tokens, how tokens are being used in terms of this retrieval, or even in terms of indexing. From indexing, because there is need of building the embeddings that you spend tokens, to indexing, to retrieval, to augmentation, because this retrieval goes to the LLM and then generate, then you need tokens because of the LLM, and then generation will happen, then tokens. So timing, scores, tokens, and then cost. So if wherever token is involved, because it's transformer and LLM, then you have to pay the cost. That is all the comes under RAG observability, and you have to involve this. Let's say if you use langfuse, right, then you can use the callback and use this method to get these all cost and values and token and traces, right? If you use Ragas, they can you evaluate all the metrics about faithfulness, recall, and you get the values. So this way you can answer anyone or you understand by yourself. So request is basically, this is how a real production trace look like. You query write, you do 120 millisecond, then embedding happens, because whenever the query you will do, that will be in text. The rewriting will happen, that will be in text. Then even when you do the rewrite that you use LLM, then you have to like change it to embeddings. That times it will take. Then retrieval will happen. It will go to, let's say, LLM and try to not LLM, go to the RAG vector database and try to grab some answer and try to produce it over here. Then we try to figure out the vector similarity with cosine, dot product, and Euclidean distance. Then reranking will happen to make sure that it's very close. Then we'll build a context, because once we have the output after reranking, we'll send it to the LLM and try to build the context, and then LLM will answer, and that will answer will come. And so combining this will all the timing and metrics will come. Hope I'm able to answer about observability. Then we talk about security. RAG security is also important, because you try to build an LLM based RAG agent where this is RAG or database is connected, vector database is connected, correct, and input comes in and output goes out, or even it connects with another set of agents, right? Then there is these are problem, data poisoning. Let's say that someone is trying to upload a PDF where malicious docs in the index, that happens. We have to control that ingestion. We have to make sure that every data that comes inside our LLM treated as a data, not as an instruction. And this is the way, if you try to treat this data as instruction, then your LLM and system prompt will be corrupted. They will try to send all the information. Indirect injection, retrieval text gives order, treat as a data. Again, in the previous tutorial you have seen, there is in prompt engineering tutorial, you must see that, where I talk in detail and also ran hands-on Python code, where we talk about system prompt, user prompt skills, right? Once we build the system prompt, then we write these texts, right? And then comes this JSON, or not JSON, value, like let's say user message, correct? This user message must be as treated as a data. Look, there are multiple ways to solve it. What we do is we do delimiter, right? That we have already told you. We do, let's say, a tag, like let's say untrusted data, correct? And then and we also write in below line that treat the above as a data rather than instruction. There is a permission link, because this access control list is there, ACL, right? And RBAC and ABAC is also there. I'm forgetting the full form of it. RBAC is rule-based access control. ACL is access control list. We try to define who can access this data, the RAG. That can happen with metadata also. In the metadata, you tell it that which kind of user permission it has. You can build a tuple, and it's a literal where you say that this is for admin, this is for viewer, this is for editor, and that gets passed into the chunk of the vector embedding. Once these chunks will be retrieved, then you do a wrapper and try to read which user it's is there for, and then you don't show them. That's how you do this permission leak and RBAC and inside a company, correct? PIA exposure you can do, like it's about secret. You try to do masking, and all, secrets in a chunks. So that is ACL retrieval. Filter away permission before returning to the user. Treat every chunk as data, never instruction. That's what I told you. Control ingestion to prevent data poisoning. The ingestion once happens, like chunks when goes to your rack, right? Redact PII plus output guardrails. So you also all the time you try to build this complete framework. You try to build the guardrails. Guardrails are really important, right? Now let's talk about production rack. Okay, so I think we have already covered it. The full engineering system, ingestion, right? You try to take a document, correct? You chunk them. There are 20 plus chunking techniques. You take it, one chunk, you apply metadata, right? And you index it. Where? Vector database, correct? Vector DB, correct? And there, all these ANN logic gets applied, and that get indexed. Chunking, already told you. Embed means these chunks will be embedded with, let's say, OpenAI small embedding model, and there are other models also, Titan, AWS, Cohere, other models also there that you can do. Then once this is indexed, that becomes a one part. Then what we do to try to retrieve it. That R is there, retrieve. you try to get the data with, let's say, hybrid search. Correct? It comes under LLM, sorry, BM25, and then you do semantic search, right? You do semantic similarity, you do reranking, you do metadata filtering, and there are other ways like you do query writing. So before, just while applying the retrieval, whatever you do that comes under retrieval mechanism, then you re-rank it. So what happens once there is, let's say, there is this is R, then there is augmentation happen. Augmentation is whatever has been retrieved will go to the LLM, correct? Then LLM will read the out data. Then it will, this is read read by LLM. LLM will read it. That is augmentation happen. Then generation will happen. Then LLM will try to generate it. Once LLM will try to generate it, LLM will generate, correct? Once it will generate from the answer that it has got from the retrieval and augmentation, and they try to write the answer. Once it will produce the answer, then there are other techniques that we apply. We apply grounding, we apply abstaining, and let's say even once the retrieval will come, it gives the data to the LLM to rewrite, then we apply re-ranking, right? That is over here. After re-ranking, we apply grounding, and then we cite it that from exactly where this is coming from, and then we evaluate it. You understood the recall, the faithfulness, correct? Cultivate out and then monitor it with permission, throughput, and also we care about this RABC, role-based access control, and we talk RBAC here. This is RBAC here, right? And then we talk about access control list. We build metadata like whom this chunk should be available of. We'll try to index it. Also, we can do that, right? And this way, we try to build a complete RAG. And now the hybrid search, re-ranking plus context engineering, access control, citation on every answer, freshness, re-indexing in pipeline, evaluation, observability and guardrails, caching, cost and latency budgets. So this was what in embedding search and RAG, right? And there is enterprise RAG that we'll see in the next video, okay? And we'll also do hands-on. We'll try to do 2-3 things. We'll try to first write code in Python, correct, with LangGraph to build a RAG, a very basic RAG, so that you understood it. And then we can also do an N10 workflow for these kind of RAG system, right? And we also look at all these theory. So let's see what exactly is remaining in this theory. Let me open this. So there is enterprise RAG architecture, right? There is enterprise ingestion document. All these things we'll understand, right? Okay, thank you. Hope you like. Make sure to comment and subscribe. Thank you.